In this video, we'll take a small detour from the second-order differential equations that describe the oscillation. This class of equations are called the Euler-Cauchy equations. Let's do a very quick recap on the regular second-order differential equations. What we covered last time was my double prime plus cy prime plus ky equals to 0. Just for comparison, for Euler-Cauchy equation, it can be expressed as x squared y double prime plus ax y prime plus by. You can see the differences. For this type of problems, we can set y equals to x to the power of m. Then y prime will be m times x to the power m minus 1. Then y double prime will equal to m multiplied by m minus 1 multiplied by x to the power of m minus 2. Substitute y prime, and y double prime back to the original equation, you'll have this expression. Note, in the new expression, we have x squared and x to the power m minus 2. We also have x and x to the power of m minus 1. In this case, we can condense the expression and write the entire equation as a function of x to the power of m. X to the power of m now is a common factor. We can just take that out, and we'll have an expression as a function of m. And this equation here is called the auxiliary equation. Thus, there are two solutions for m1 and m2. I'm not reading out the expressions. Here, we face three cases. In the first case, the part in the square root is positive. Then we'll have two distinct m values, and these two m values are real. y1 is simply x to the power of m1, y2 is x to the power of m2. We also know that any linear combination of those two solutions is also a solution. So the general form of the solution is y equals to c1 x to the power m1 plus c2 x to the power of m2. In the second case, m1 equals m2. What this tells us is the part in the square root sign is equal to 0. The solution for y is simply x to the power of half 1 minus a. There also exists another linearly independent solution. The solution can be written down as log x multiplied by x to the power of half 1 minus a. Again, the linear combination of these two solutions is also a general solution. In the third case, we also have m1 not equal to m2, but in this case, we have the complex solution, that is, the part in the square root is negative. We will not cover this in details as this is less important. Let's look at one example. For case 1, we have x squared y double prime plus 1.5x y prime minus 0.5y equals to 0. In this example, 1.5 is a, minus 0.5 is b. Write down the auxiliary equation again, and plug in a and b. We'll have two real solutions for m. m1 is equal to 0.5 and m2 equals to minus 1. Sorry, I have a mistake in my written note here. m2 should be minus 1 instead of 1. The general solution thus is c1 times x to the power of 0.5 plus c2 x to the power of minus 1. In the next video, we'll come back to the second-order differential equations that describes oscillation, looking at the forced damped system.